How did the first skyscrapers survive earthquakes decades before modern seismic engineering even existed? In 1906, a magnitude 7.8 earthquake shook San Francisco for 45 seconds. It leveled 80% of the city. Yet a handful of steel-framed towers, some barely a decade old, refused to fall. The common explanation is simple. They were either lucky or massively overbuilt. But when you look closer at the heavy masonry, the riveted joints, the redundant steel frames, something far more ingenious emerges. A forgotten secret baked into every beam and rivet by builders who had no seismic codes, no computer models, and no shake tables, only instinct. And that instinct may have outsmarted a century of modern optimization. In the days after the 1906 San Francisco earthquake, newspapers rushed to explain how steel towers like the Call Building had survived when so much of the city lay in ruins. Headlines called them oversized marvels and debated whether their survival was pure luck or the result of extravagant overbuilding. The press painted a picture of buildings so stuffed with steel and brick that they simply refused to fall, as if brute force alone had saved them. Critics like John B. Hayward, a respected engineer of the era, pushed back. In a widely read column, Hayward questioned the wisdom of surrounding steel frames with what he called excessive masonry, warning that such extravagance might be more about show than safety. He argued that construction budgets were swollen by material that did little to guarantee survival. The public, caught between awe and skepticism, wondered if these towers had simply gotten lucky. But beneath the headlines and heated debates, something more subtle was happening. Builders of the time worked without seismic codes, shake table tests, or even a clear understanding of how earthquakes truly affected tall structures. Their work was guided by observation, experience, and a kind of engineering instinct, an instinct shaped by the disasters and near misses that came before. Massive steel frames, thick masonry cladding, and deeply rooted foundations were not calculated for earthquakes in the modern sense. They were the product of a mindset that valued patience, excess, and a respect for forces no one could fully measure. This approach, criticized as wasteful by some, ended up providing hidden resilience. The story of these early skyscrapers is not a simple tale of luck or reckless overbuilding. It is a story of builders who, lacking precise science, built with a margin for the unknown. Their choices, often questioned at the time, left behind structures that outlasted the odds. Looking up at these old steel-framed towers today, it's worth asking whether their survival was really an accident, or whether the secret lies in a kind of wisdom that modern engineering sometimes forgets. This wisdom remains a lesson for today. Chicago in the 1880s was a city in a hurry, its skyline rising almost as fast as its ambitions. Into this whirlwind stepped William LeBaron Jenney, an engineer with a head full of sketches and a belief that steel could lift a building skyward without weighing it down. In 1885, his home insurance building became the first true metal skeleton, a 10-story experiment that combined rolled steel columns and beams into a frame that carried all the weight, freeing the walls to become mere curtains. Jenney's design notebooks from those years are filled with calculations and rough diagrams, but what stands out is the confidence to try something no one else had dared. The appetite for height caught fire. By the turn of the century, San Francisco was racing to catch up, determined not to be outdone by the Midwest. Between 1898 and 1902, the city saw more than 30 steel-framed projects break ground, each taller and more daring than the last. The rivalry wasn't just about civic pride. It was about who could master the new material, who could build faster, higher, and with more flair. Every new tower was a gamble. No seismic codes, no wind load formulas. Just the judgment of engineers and the lessons of past failures. Construction moved at a pace that would be unthinkable today. Crews worked around the clock, hoisting beams into place with steam-powered derricks, riveting connections by hand, and wrapping the frames in thick layers of brick or terracotta. The cost of steel and labor soared, But so did the demand for ever taller office blocks and hotels. Material choices were shaped as much by economic cycles as by engineering logic. When steel prices dipped, frames grew heavier. When budgets tightened, corners were cut. Yet even in this fevered environment, builders tended to err on the side of excess. Without formal codes to guide them, they relied on overbuilding, sometimes out of caution, sometimes out of showmanship. The result was a skyline that was both a monument to optimism and a laboratory for structural ideas that would take decades to fully understand. Manuals from the 1890s offered little guidance for earthquakes. Calculations for wind and gravity loads filled the pages, but seismic forces were left to the imagination. Engineers in Chicago and San Francisco worked in a world where the only certainty was uncertainty. There were no formulas to follow, no tables to consult, and no building code to enforce minimum safety against shaking. The first seismic ordinance in the United States did not appear until 1908 in San Francisco, 2 years after the city's devastating quake. Even then, the code was a single paragraph, requiring only a rough estimate of lateral force based on building weight. It would be another 23 years before the first large-scale shake table experiments at Berkeley in 1931 provided any kind of scientific feedback on how steel frames actually behaved during an earthquake. In practice, every decision came down to experience and a kind of professional instinct. The people who built these towers had only their eyes, their hands, and the lessons of the past to guide them. Iron workers listened for the right ring of a rivet head. Foremen watched for hairline cracks in fresh brickwork after minor tremors. If a building settled unevenly, they recorded it in field notes and tried something different on the next project. The absence of formal standards meant that each engineer became his own authority, drawing on a blend of caution and bravado. Some responded to uncertainty by adding more steel, more masonry, or deeper foundations than the numbers strictly required. Others trusted the skill of their crews to improvise solutions on the fly. This era of guesswork and overbuilding may seem reckless by modern standards, but it produced structures with a built-in margin for the unknown. The resilience of early skyscrapers was not the result of precise calculation, but of a mindset that accepted what could not be measured. Only later would science catch up, codifying what builders had learned by feel. Looking back, it is clear that the survival of these towers was less about luck and more about a quiet, persistent respect for forces no one could fully predict. 23 cubic feet of limestone per floor by modern standards, that sounds like extravagance. Yet for the builders who wrapped Chicago's and San Francisco's earliest steel skeletons in thick layers of stone and brick, this was simply how things were done. The heavy cladding, often ridiculed as unnecessary weight, played a role few at the time could have articulated. It acted as a kind of silent partner in the building's survival during an earthquake. Masonry cladding was not chosen for its seismic performance. Fireproofing and civic pride drove the decision. Stone and brick gave these new towers a sense of permanence and grandeur that steel alone could not provide. But when the ground shook, that very mass became an unexpected asset. The thick walls, anchored to the steel frame with flexible shelf angles and iron ties, moved just out of phase with the skeleton behind them. As the quake's energy raced through the city, the masonry lagged slightly behind the steel, absorbing and diffusing the shock. Each brick and stone, tightly packed yet able to slide microscopically, helped to dampen the building's sway. This was not the brittle, monolithic masonry of old. Instead, it was a layered system, steel for strength, masonry for mass, joined together by fastenings that allowed just enough give. Contemporary ledgers for the Call Building and Mutual Savings Bank record staggering quantities of cladding, 30 cubic feet of brick per floor, 2 million pounds of granite and terracotta on the Board of Trade. These numbers, dismissed as architectural showmanship by critics like John B. Hayward, now reveal a hidden logic. The inertia of the cladding increased the building's response time to violent shaking. Laboratory tests a century later would confirm what builders only sensed. When properly anchored, heavy masonry acts as a damper, bleeding off energy that might otherwise tear the frame apart. The method of attachment mattered just as much as the material. Iron shelf angles bolted to the steel beams supported the weight of the stone and allowed it to move independently in small increments. Flexible ties, often spaced every few feet, kept the veneer from peeling away but did not force it to act as a rigid shell. This subtle separation allowed the facade to crack and absorb energy without transmitting the full force of the quake to the skeleton inside. Period manuals describe the practice as a way to relieve settlement stresses, but in practice, it introduced a form of controlled flexibility that modern engineers would later recognize as essential for seismic damping. The concept of damping, reducing the amplitude of vibration, was not part of the engineering vocabulary in 1906. Yet the combination of mass and movement in these early towers achieved exactly that. The cladding's inertia, coupled with its flexible fastening, created a first line of defense against unpredictable forces. Modern seismic design now uses tuned mass dampers, pendulums, and viscous couplings to accomplish what those early builders achieved with limestone and brick. Looking at the numbers, 23 cubic feet of stone per floor, millions of pounds of masonry, one might still be tempted to see only excess. But the survival of these towers suggests something else, a practical wisdom born of experience and caution that built resilience into every layer. The heavy cladding, far from being a relic of outdated thinking, was the first shield against disaster, a hidden strength that allowed these steel-framed giants to endure when so many others fell. Their survival reminds us that sometimes what seems like overbuilding is really an unspoken respect for the unknown, expressed in stone, steel, and the patient craft of those who refuse to take chances with the forces they could not see. Steel was the currency of confidence in the early age of skyscrapers. When George A. Fuller's company took on the Call building in San Francisco, they ordered more than 11,200 tons of steel for a structure that, by modern standards, could have stood with nearly a third less. This was not an isolated case. Across Chicago and the West Coast, ledgers from the turn of the century show steel frames routinely oversized by 30% or more compared to what today's codes would require. At first glance, this seems like architectural bravado or financial waste, a race to outbuild rivals with sheer mass. But the numbers tell a subtler story. Within each floor of the Call building, a dense lattice of beams and columns formed a continuous grid. The pattern was not just for show. Every joint, every splice, every redundant member created a safety net. If a column or beam gave way, whether from fire, earthquake, or human error, the surrounding frame could reroute the load through alternate paths. Modern engineers call this redundancy. In practice, it meant that no single failure could bring the whole tower down. Fuller's own construction memos, saved in company archives, reveal a philosophy rooted in caution. He wrote that the cost of redundancy is far less than the cost of failure. His teams designed for the unexpected, not just the expected. In retrospect, this mindset created buildings that could absorb shocks well beyond their original calculations. Recent drift studies using computer models retrofitted to these old frames confirm what the builders sensed by instinct. When engineers simulated the sudden removal of 25% of non-critical steel members, essentially erasing a quarter of the structure's skeleton, the resulting increase in sway or story drift was only 12%. The frame flexed, but it did not break. For comparison, modern seismic codes allow up to a 30% drift rise before a building is considered at risk. This means that the early towers, built without seismic science, already surpassed today's standards for ductile performance. The Call building's steelwork was not just heavy, it was interconnected. Redundant framing allowed energy from an earthquake to spread out, dissipating force across hundreds of joints rather than concentrating it at a single weak link. In the language of structural engineering, these towers had multiple load paths, routes for gravity and lateral forces to travel safely to the ground, even if part of the network failed. This surplus was not always deliberate. Economic swings, fluctuating steel prices, and the absence of strict codes sometimes drove builders to err on the side of excess. But the result was a kind of accidental genius, frames that could tolerate damage, adapt to shifting loads, and remain standing when less generous designs would not. Today, when engineers study the performance of these early skyscrapers, they find that the massive redundancy built into their bones is not just a relic of past extravagance. It is a structural safety net, a buffer against the unknown. The survival of these towers is a lesson written in steel. Sometimes, building more than necessary is the wisest response to forces we cannot fully predict. And when the ground shakes, it is not luck that keeps a building upright, but the quiet strength of surplus and the foresight to expect the unexpected. Beneath the soaring frames and heavy cladding of early skyscrapers, the real battle for survival played out where steel met earth. In Chicago and San Francisco, soft ground posed a challenge that no amount of overbuilding alone could solve. Bedrock often lay far below the surface, sometimes as deep as 70 feet, while the upper layers were made up of clay, silt, or reclaimed fill that could shift or liquefy under a strong quake. Builders turned to foundation systems that were as bold as the towers themselves, blending old-world methods with new experimentation. The home insurance building in Chicago rested on a raft foundation, a thick slab of concrete spanning a grid of timber piles driven deep into the lake bed. This floating mat spread the building's weight over a wide area, allowing it to settle gently into the soft ground rather than tip or sink unevenly. Engineers didn't have formulas to predict soil behavior under seismic loading, but they knew from experience that a wide, flexible base could ride out minor shifts without cracking. Field notes from the era describe how crews watched for subtle signs of movement, hairline cracks in the basement, doors that stuck after a rainstorm, and adjusted their methods accordingly. If a building settled too much, the next project would get more piles or a thicker raft. San Francisco's engineers faced an even trickier puzzle. The city's downtown sat atop layers of loose sand and clay, prone to sudden liquefaction when shaken. For the Call building and its piers, builders drove timber piles as deep as 30 feet, then capped them with concrete grillages or caissons. These caissons acted like giant plugs, anchoring the steel skeleton to the most stable soil they could reach. In some cases, the piles extended even further, 70 feet or more, seeking a firm layer that could take the load without shifting. The intent was not to create absolute rigidity, but to allow the entire structure to move as a unit if the ground itself gave way. The 1906 earthquake put this approach to the test. While many brick and timber buildings collapsed when their shallow footings failed, the skyscrapers with deep caissons or floating rafts largely survived. The Call building's foundation, for example, absorbed and distributed the quake's energy, limiting settlement to just a few inches, enough to crack some plaster but not enough to threaten the frame above. Contemporary reports from the California State Engineer noted that these deep footings absorbed the bulk of the shaking without noticeable settlement. This was not luck. It was the result of a philosophy that saw the ground as an unpredictable partner, one to be respected, not ignored. Builders hedged their bets with deep, redundant foundations, even when the cost was high and the science incomplete. They were not chasing efficiency. They were building for uncertainty, guided by the lessons of every structure that had settled, cracked, or failed before. The ingenuity of these foundation systems, caissons, rafts, floating slabs, created a silent resilience, allowing the towers above to flex and settle without catastrophic loss. In this way, the secret of early skyscraper survival began not in the steel above, but in the patient, cautious work that vanished beneath the city streets. Riveted joints, often overlooked in the story of early skyscrapers, performed a subtle but vital role in holding steel frames together. Each rivet began as a glowing steel pin, hammered into a hole deliberately made 2 or 3 millimeters wider than the shank. This tiny gap, almost imperceptible, allowed for a controlled slip. Just 0.1 to 0.3 millimeters, before the rivet pressed fully against the steel. In the chaos of an earthquake, these minuscule movements multiplied across thousands of joints, providing a hidden flexibility that let buildings sway without tearing themselves apart. The secret lay in the plastic heads of the rivets. Heated and hammered, the steel shank hardened but remained ductile, able to stretch and deform under stress. Forensic studies of buildings that survived the 1996 San Francisco earthquake revealed rivet shanks with necking and local shear, clear signs that these connections bent and yielded, but rarely broke. Each rivet acted as a tiny fuse, absorbing shock and dissipating energy before passing the load along. Modern tests confirm the strength. A standard 3/4-inch rivet can resist about 3,500 pounds of shear. But the real advantage wasn't brute force. It was the ability to yield, to flex and recover, rather than snap under pressure. Redundancy was built into every connection. A single splice between beam and column might be held by 20, 30, or even 40 rivets. If a few slipped or yielded, the rest took over, spreading the stress and preventing catastrophic failure. Later, when engineers compared these old riveted frames to modern welded or bolted joints, they found a stark difference. Welds and bolts, with their tight tolerances and rigid seams, often failed suddenly under seismic loads. When a welded joint cracks, it does so without warning. Riveted joints, by contrast, yielded in stages, buying precious seconds for the building to ride out the shaking. Iron workers of the era trusted their instincts. Oral histories from Chicago recall the importance of a rivet that would sing when struck, a clear note that meant the head was seated just right. Manuals from the 1890s called for oversized holes and careful hammering, not for earthquakes, but to allow for construction tolerances and thermal expansion. Yet this practice created joints that could slip and yield, a feature modern engineers now try to recreate with slip-critical bolts and flexible welds. What looked like old-fashioned craft was, in fact, a sophisticated form of resilience. The micro-movements of riveted joints, their capacity to slip, yield, and recover, transformed steel skeletons into structures able to survive forces no one could yet measure. This quiet flexibility, born of practical skill and cautious excess, became the hidden fuse that protected early towers from disaster. At 5:12 a.m. on April 18, 1906, San Francisco was jolted awake by an earthquake that lasted 45 seconds. The ground heaved with a force exceeding 0.4 G, enough to threaten even modern buildings. Entire blocks collapsed or burned, but a few steel-framed towers remained standing. The Call Building and Mutual Savings Bank, both in the heart of the fire zone, kept their structural frames intact. Their facades cracked, but the steel skeletons inside held firm, absorbing and redistributing the shock. Just a block away, the Valencia Street Hotel collapsed, killing dozens. Timber warehouses near the waterfront crumpled as their shallow footings failed. The steel towers, considered overbuilt at the time, outlasted their neighbors. City engineer Eugene Gilmore inspected the ruins and found the Call Building's foundation had settled less than 3 inches, despite unstable fill beneath. All major columns stood plumb. The steel frame flexed but did not break. Gilmore's report listed the survivors: Call, intact; Mutual Savings, intact; Merchants Exchange, minor damage. He wrote that the difference was not luck, but continuous framing and deep footings that allowed the structures to ride out the shaking as a unit. The Call Building's frame alone carried more than 11,000 tons of steel, with another 2,000 tons of masonry cladding. Every joint was secured by dozens of rivets, each able to yield slightly under stress. When the ground motion peaked, these connections slipped and recovered, dissipating energy that would have shattered more brittle systems. Gilmore's field sketches showed bowed columns and shifted beams, but the frame remained locked together. In contrast, the nearby warehouse, built with unreinforced brick and shallow footings, collapsed instantly, its walls unable to flex or absorb the shock. Those 45 seconds revealed a hidden strength in early skyscraper design. The steel towers survived not because of calculation or code, but because their builders allowed for the unknown. Gilmore's inspection became the first technical proof that what seemed excessive was, in fact, resilience. Jack O'Leary felt the quake before he saw it, a shiver running through the steel, every rivet ringing out. In a letter to his brother, he described, "The girders moved like reeds in a wind, but the rivets gave way like a breath, never a snap." For O'Leary and his crew, the work was more than muscle and metal. It was a conversation with the building itself. Each rivet was set by sound, searching for a sharp ping that meant the joint would flex and recover, not break. That difference, almost invisible, could decide whether a tower stood or fell. On the scaffolds, the earthquake was immediate, a sudden sway, dust drifting from beams, the hush when a column shifted. O'Leary's 12-man crew paused after every aftershock, eyes on the rivet lines, listening for trouble. He wrote, "We trusted the steel, but we trusted each other more. If one man heard a crack, we all listened." The sense of responsibility was personal. The tower's fate depended on thousands of choices, each made with a mix of caution, pride, and respect for what they couldn't control. Martha Delgado, a mason at the Fairmont Hotel, learned from her father how to set granite so it would flex, not fracture. She described laying interlocking joints, each stone set to give a little, just enough so the building could dance on the mud. In oral histories, Delgado spoke of finding her place on an all-male crew, insisting on careful spacing between granite panels, a hair's breadth that let the facade move with the earth. Her technique became a quiet insurance policy, a way to let the building breathe. Stories like these, saved in letters and family lore, reveal a different kind of engineering, one that lived in the hands and instincts of those who built these towers. The resilience of early skyscrapers was as much about patience and craft as it was about steel and stone. When the ground shook, it was these invisible choices that let the towers endure. Modern engineering promised efficiency, but the results have sometimes been less than reassuring. In the aftermath of the 1994 Northridge earthquake, inspectors found that dozens of supposedly state-of-the-art steel moment frames in Los Angeles had cracked or failed. These were not century-old towers overloaded with masonry and redundancy. They were lean, optimized structures designed to meet the letter of the code with as little material as possible. Engineers had trimmed away what they saw as excess, using up to 30% less steel than their early 20th century counterparts. The logic was simple: lighter frames, lighter costs, same safety. But when the shaking started, the frames proved brittle, their welded joints snapping without warning. Curtain wall systems, prized for their sleek profiles and minimal structure, offered little resistance to lateral forces. The damage was so widespread that entire buildings had to be evacuated, and the U.S. Bank Tower, an icon of modern design, became a case study in the risks of chasing material efficiency over resilience. The irony was hard to miss. While the old giants stood on their surplus, the new towers, stripped to their minimums, showed how easily efficiency can become fragility. The lesson was clear. The margin for the unknown, once built in by instinct, cannot be wished away by calculation alone. Modern seismic codes carry the fingerprints of the riveted era, even if most engineers no longer swing a hammer at red-hot steel. Provisions like ASCE 716 slip critical connection requirement, mandating that bolted joints allow for controlled micro-movement before full bearing, echo the old practice of oversized rivet holes. This clause is not just about strength. It is about letting a joint yield and absorb energy, just as riveted frames once did. In the same codebook, redundancy is no afterthought. The AISC 36016 specification carves out entire categories for structures with multiple load paths, demanding that no single failure can bring down a frame. These rules, spelled out in technical language, are the scientific heirs to a philosophy that once relied on extra steel and a craftsman's ear for the right ring of metal. Hybrid joint research now explores connections that blend the slip of rivets with the strength of high-tension bolts, a deliberate nod to the accidental genius of the past. Each new clause in the code is a quiet tribute to lessons learned from towers that flexed and survived. The continuum is clear. What began as instinct and overbuilding has become codified resilience, ensuring that the wisdom of early builders is never truly forgotten. Today, every steel-frame skyscraper that still stands from that era is a testament not to luck, but to a mindset that valued margin, intuition, and humility before nature's unknowns. As modern engineering increasingly optimizes for efficiency, the old towers remind us, sometimes, survival comes from honoring what we can't fully predict. Their resilience is not just history, it's a silent challenge for every structure we build today. Next time you pass one, consider what it truly survived.